that I get a copy of the question. Principal quantum number n equals 4. The question is, why are there 7 f orbitals? Okay, so if you can just see this PDF file here, n equals 4. Okay, the allowed values of L for n equals 4 are 3, 2, 1 and 0. What you're looking for there. In terms of the angular nodes, okay, fxz squared orbital. I put the picture up on the screen, so I guess everybody noticed that one. And shown in this one here, okay, you can see that the lobes change colour from blue to gold, okay, 3 times. So there's an angular node here, one here, and one here. So you're expecting 3 for this one, so you should have got 3. The one that's a little bit more difficult is this one shown here. This is the fx cubed orbital. So all f orbitals should have the same number of angular nodes. Okay, so if the one you've just done has 3, the next one must also have 3. One of them is very easy to spot, okay, because it goes right through the middle of the orbital, just slices it in half. The other two, strictly speaking, okay, they're not planes, rather they are cone-shaped. So I think you can see here as I've drawn it, that's the nucleus in the middle, and between this blue part here, lift it up a little bit, okay, it changes from blue to gold there, so it's kind of a cone-shaped surface there. And if there's one on this side, there is also one on that side as well. So it's a little bit like a dz squared orbital, which I guess you've considered previously, okay? So in each case, you're expecting 3. For one of them, it's relatively easy to point out. So those 3, and then the other one is shown here as well. Okay. In terms of the radial nodes, we've talked about this a little bit in the lectures. Let's see if I can find the graph for you. So in terms of the radial nodes, for 4f orbitals, it's relatively simple, I think. Okay, so this graph I explained yesterday, there is a 4f orbital. A radial node, okay, there is some value of r in the radial part of the wave function at which the wave function changes sign. You know, drops to 0 and becomes something else. For a 4f orbital, I think you can see, if you follow this up here, and then down the other side, there are none. Okay, a 4f orbital has 0 radial nodes, okay, which you would expect if you take the maximum value of L for a given principal quantum number, that orbital always has 0 radial nodes. Okay, so 1s, 2p, 3d, 4f has 0 radial nodes. For a 5f orbital, it's slightly different. Okay, so a 5f orbital starts here, it goes up, then it goes down again and reaches 0. Okay, that point there for a 5f orbital is a radial node. Okay, so then it goes back up and then tails off. So this one has 1 radial node, that one has 0. So the next part of the question talks about electronic configurations. Okay, so I won't tell you this. Is anybody moved on to question 2? Not yet. Okay, so I won't tell you the answer to this one. The question is, why does this element and this element have slightly different electronic configurations compared to the general? Okay, so these are the configurations I'm trying to do. So I'll think about that. I'll talk through the answer of each second. then of the lanthanides. Where did we get to? So the one that I guess is fairly straightforward is lutetium. Okay, so the reason you have to populate one of the d orbitals down here is that now your F shell is filled, so the electron has no option but to go into here. So that's why that one behaves as it does. For gadolinium, okay, this one kind of sits in the middle of two lanthanides that display the traditional configuration. Here, on the other hand, your 5d electron, it could go in there, but the problem is you would convert an F7 configuration into an F8 configuration, and that is bad because you break the half-shell stability, which has all sorts of energetic implications. If you think about gadolinium in F7, you have 7 F electrons all pointing in the same direction, yes? If you take electron number 8, if you place it in with those 7 electrons, the spin points down, which means it can pair up with all of them, okay? So the electrostatic repulsion is then effective, the effective nuclear charge, and this gives rise to things like the lanthanide contraction, which we talked about. Interestingly, although the energies of each of these orbitals decrease as we go across the series, they don't all decrease at the same rate, which is something we discussed yesterday. The one that goes down very quickly, however, is 4F. So when we're talking about cerium, okay, what we have is a configuration that looks like this, or like this here, okay? With your 5d electron, you could, if you wanted to, put it down here. If you do that, that's the only way it is that would be okay, so the spin is pointing in the same direction. What you're doing is moving an electron from an orbital manifold where it's not interacting with any other 5d electrons. What you are doing is putting it down here where it can interact with another 4f electron, and actually quite strongly. So this is a strong repulsion, which is, that will cost you energy to do that, to pair electrons in the same orbital manifold. If, on the other hand, you move it back up here, you get rid of the repulsion, but you incur additional energy, okay, because you're using a higher energy orbital. The question is, which is the biggest destabilizing influence? And actually, it turns out to be this situation here. So the configuration is really very key to move this electron away from this one, even if it's into a higher energy orbit. So that happens for cerium. You may wonder why, when you get past cerium to praseodymium, that doesn't happen. Okay, you move to the regular situation, you have this and this. It turns out to be the case, and you may not predict this based on what you already know, that by the time you get to praseodymium, the separation between these two is now sufficiently large to stop this from happening. Okay? And then that establishes the pattern for the rest of the series. So for gadolinium and for lutetium, it's are people now working on question 2? Okay? What we'll do is we'll consider question 2 today. We're going to do it for under 10 minutes, if that's okay with you, and then we'll finish for today. And what we will do is consider the other questions in a workshop later in the course. Okay? So if you make some progress with question 2, when you get to about 10 past 4, I'll tell you what the answer is. Okay, some people have almost finished question 5, actually, which is quite impressive, so people are doing well. Okay, so the question 2 then, to give you some insight into the answers. Okay, so this is what we have here is a written version of the answer sheet, which I will provide you with when the course is finished, so you can have more detailed answers. Okay, but the lanthanide contraction, in principle, should not take you very long to define. As we've all seen, it's a gradual decrease in radius as we move from left to right across the series, and that's it. That is the contraction. Okay, so hopefully everybody is fine with that one. That question there is from a different lecture course, so I'll go back to the spin-orbit coupling one here. So the term spin-orbit coupling we've talked about a lot today, and it is simply a case where the total spin contribution and the total orbital contribution couple together to give a different spin-orbit coupled angular momentum. And the spin contribution and the orbital contribution can either work together or they can work against each other depending on where you are in the F-Mach series or elsewhere. Okay? So the quantum numbers are S and L for the spin and the orbital bit, and then the spin orbit coupled quantum number is J, which you can work out from a simple arithmetical sum. Okay, so which I guess that's it. Periodic variation in the spin orbit coupling constant zeta. Generally speaking, it increases with atomic number. So for lanthanides, it looks like this. So for cerium, it starts off at 644, and ytterbium down here 2,883. So it gets bigger as you go down the series. And the same is true for the series of 3D elements as well. It increases from left to right. Fine. So how about the values here then of zeta compared to transition metals? Go back up a few slides. So a typical value of zeta for a first row transition metal ion is no more than a few hundred wave numbers. Whereas for a lanthanide, okay, over 1,000 wave numbers is pretty common. So the spin orbit coupling constants for lanthanides are much higher than for 3D transition metals. Okay, I emphasize they're 3D. Okay, what implications does this have for the electronic structure of 4F and 3D complexes at room temperature? That's room temperature in Manchester, by the way, not in India. So 293 Kelvin. What that means, so for transition metals, the crystal field splitting is the dominant interaction, and then we consider spin-orbit coupling in a secondary manner. Okay, the crystal field splitting can be 10 to 30,000 wave numbers for titanium, which is clearly orders of magnitude larger than it was with the free ions. Then we move to lanthanides. The crystal field splitting is really quite pathetic, okay, only a few hundred wave numbers. So that means then that your spin-orbit coupling is the dominant interaction, and we regard crystal field splitting as a second-order minor perturbation. So that means then as we move through a crystal field splitting diagram for a lanthanide, it looks like this. Electron repulsion, spin-orbit coupling is a dominant interaction, and the crystal field splitting down here is a relatively minor perturbation. But nonetheless, as we said in the previous lecture, that is important for low temperature magnetism. Okay, we've done a lot today, so your brains must be aching a little bit, certainly my voice is. So we will finish there for today, and we will pick up the story tomorrow. I look forward to seeing you there. Thank you. Hi. Yeah.